Hi everyone, this is the video lecture of section 6.1. More about areas. Okay, this is a rather short section. Let's say you will find the area of the region bounded by two curves. Therefore, two equations. Let's see. So x-axis is going here, y-axis is going there. From A to B. Let's say this is y equals f of x, y equals g of x. Okay. In section 5.1 and 2, we find that if your function f of x is always greater than or equal to 0, the area of the region between y equals f of x and the x-axis, and x equals a, x equals b, was definite integral. Right? By using this approximation, limit of the Riemann sum. Right? Likewise, we can do the same thing here. We can split the x interval uniformly, let's say x1, x2, this is xi minus 1 xi. So we just approximate area of the region by using Riemann sum, which is area of these, right, rectangular columns. These rectangular columns. The ith subinterval between xi minus 1 xi will be given as, look at this. We are evaluating, this is xi star, f of xi star here. Let's say this is same xi star, g of xi star. Okay? Then the area of the ith rectangle G, delta x, that is the width, which is b minus a divided by n. We are dividing the interval a to b into n equal subintervals. So b minus a. And the xi equals a plus I times delta x. And we choose any sample point between xi minus 1 xi, ith subinterval. And there we're gonna, at xi star, we calculate function f and g value. Then the height of the area is base times height. Your height of the rectangular column is this y coordinate minus this y coordinate. That means f xi star minus g xi star. All right? So some of the areas of such rectangular columns will be from 1 through n, f of xi star minus g xi star times delta x. That would be an approximation of the value of the area. Now, the larger the n, the more division you take, the better the approximation. And if you take the limit as n goes to infinity, that will be the true value of the area. What is this? This is Riemann integral of the function f minus g at xi star. So this is a definite integral, linear Riemann sum of this function. So that is exactly definite integral function f of x minus g of x dx. So if you want to find the area of the region bounded by y equals f of x graph, y equals g of x graph, from x equals a to x equals b, then you will have to evaluate this definite integral. Obviously, we are assuming that always your f of x is above g of x graph for all x between a and b. Okay, assuming this. So f, you can call f is a upper function, g is a lower function. Upper function minus lower function will give you height function, right? It's the integration of a height function will give you area. Now it turns out that this is a special case of this. This is between y equals f of x and y equals 0. So your g of x is just happen to be constant 0 function. So when you have a constant 0, you will get this one back, right? Okay. So now let's do some example. Some remark. Now this one can be split as, we learned that definite integral can be split over additional subtraction. Constant can be taken out of the definite integral. Now, if you consider special case, let's say both, let's consider this special case, okay, on this interval, okay? This is a remark. Now, what is it? Let's say this is function f graph. Let's say this is function g graph. Now, the first integral will be area of the region between graph of f and xx. The second integral gives you the area of the region between g and x-axis. If you subtract this red area from the blue area, you're going to get the area of this region. That's precisely the region we're talking about, the region between graph of f and graph of g, between a and b, right? So this one is consistent. Okay, let's do some examples. So, example 1. Example 1. Find the area of the region bounded by BDD, means bounded. Okay, bounded. So BD stands for bounded. Bounded by the graph of A. Y equals cosine of x. Y equals x minus pi of h. And x equals 0 and x equals pi of h. B. Between y equals x squared and y equals 4x minus x squared. Okay. Now here, first, A. A cosine graph going from 1 to 0, between 0 and pi of h. This is pi of h. This is 1. Okay? Now, the other graph, g, y equals x minus pi of h. Slope 1, y-intercept negative pi of h. So if you start from negative pi over 2, slope 1, you go by pi over 2, pi over 2. So you're going to go through x-intercept pi over 2. Okay? Between x equals 0 and x equals pi over 2, they happen to just intersect there. That's fine. So we want to find the area of this region. So our upper function in this case is cosine of x. Lower function is x minus pi over 2. So the area is from 0 to pi over 2, 0 to pi over 2, upper function cosine of x minus lower function x minus pi over 2 dx. Okay? So this will be definite integral of from 0 to pi over 2 cosine of x minus x plus pi over 2. I just distributed this minus. Now, then cosine x antiderivative is sine of x between 0 to pi over 2 minus 1/2 of x squared between 0 to pi over 2. This one is pi over 2 times x between 0 to pi over 2. Okay? So sine pi over 2 equals 1, sine of 0 equals 0. 1 minus 0 minus 1/2 pi over 2 squared, which is pi squared over 4 minus 0. Okay? Plus pi over 2 minus 0. So it's going to be 1 minus pi squared over 4 times 1/2. So pi squared over 8 and multiply pi squared over 4. Okay? Now, this one is 2 pi squared over 8 minus 1 pi squared over 8. So together, take a pi squared, and in the parentheses, you'll have a minus 1/8 plus 2 over 8, which is plus 1 over 8. 1 plus pi squared over 8. Okay? So, simple application of this result. Okay? Definite integral of upper function minus lower function. Now, B. Y equals x squared. Y equals minus x squared plus 4x. If you take a minus x, then x is minus 4. So, opening downwards with x-intercept 0 and 4. And then when in the middle, when x equals 2, you will get minus 2 minus positive 4. So 4. So this will be the graph going through 4. And y equals x squared. Going through 0, 0 to 2, 4, right? Actually, it's going through this. So, between 0 and, so the area between, bounded by these curves, will be this. This is the region we're talking about. In that case, which one is upper function? This one or this one? For given x, obviously this is upper function, right? The graph of upper function, which is y equals 4x minus x squared. Lower function is y equals x squared. Okay? So, your area should be from 0 to 2, upper function minus lower function. So 0 to 2, 4x minus x squared, so minus 2x squared, integral from 0 to 2. 4x. X integral is 1/2 x squared. So 2x squared from 0 to 2 minus 2/3 x cubed 0 to 2. Okay? So this one will be 2 times 4 minus 0. 4 minus 2/3. 2 to the third is 8 minus 0, so 8. 8 minus 16 over 3. Now a equals 24 minus 8 minus 16 over 24 minus 3 minus 16 over 3. So 8 over 3. Okay, that would be the area of this region. All right. Okay. Then next example. Next example 2 is same as example 4 on your textbook on page 434. Page 434. I'm not going to copy the problem because it is already written on the text in the textbook. So interpret the area between velocity curves, right? Figure A shows velocity curves of two cars, A and B. They move along the same road, side by side. What does the area between the curves represent? So you have a velocity curve for car B here, and velocity curve for car A is like this. They ask you to find the area and the meaning of the area of this region. Okay? So this is from 0 to 16 seconds. T seconds. And this is miles per hour. Miles per hour. So the area is, again, from 0 to 16, b of a upper function minus lower function, dt. And that is 0 to 16. Okay, let me just check the video. Okay. b a of t minus b of t dt. All right. That is dt. The area of the v of velocity function, when velocity is non-negative, that will be, integral velocity is displacement, right? This is displacement from 0 to 16. Because everything is positive, that means the distance. Distance traveled by car A, the first one, minus distance traveled by car B. So A is a high velocity, so definitely go further. Distance car A made minus distance car B made. Difference will be the distance between two cars 16 seconds later, right? This is distance between A and B at the final time 16 seconds. Okay? So So the meaning of that area is nothing but the distance between two cars, because we are given velocity function of two cars. Now, they ask you to use Simpson's rule, okay, to approximate this area. And unfortunately here, it gave you miles per hour versus seconds, so it does not match. So you have to change this one, miles per second or feet per second. If you want to find the distance between two cars in feet, you have to convert this one feet per second. So 1 miles per hour, apparently, same as, because mile is 5280 feet, hour is 3600 seconds, feet per second. Using this conversion, and then your textbook kindly read the values at every 2 seconds. Okay? So this value, this value, this value, this value. Okay? So that's what you have here in the table. Alright? Every 2 seconds. What we need is this value. Right? We have to integrate. This is the one we are going to integrate. We are not going to do it separately. So they gave you this value. The fourth row give you velocity difference at every 2 seconds, right? So then, using Simpson's rule, remember Simpson's rule from 5.9, you have in this case, we try to use Simpson's rule. S8. We're going to use S8 with n. N equals 8. That means delta t equals 16 minus 0 over 8. 2 seconds. The size of the subinterval. And your Simpson's rule says that delta t over 3 times first value. So let's say I'm going to call this function as f of t. Difference of two velocities. We're going to call it f of t. So f of 0, 4 f of 2, and 2 f of 4. 4 f of 6, 2 f of 8. Simpson's rule. 4 f of 10. 2f of 12 plus 4f of 14, and the last one. The first one and last one will be just 1, 1, and then odd terms will be 4, and then even terms will be 2 here, the coefficients. So then you have to just plug it in, all these values. Then those values, if you plug it in, that'll be 2/3 0 plus 4 times 13 plus 2 times 20. $29 plus 4 times also 29, 30. Okay? You just copy these values from the table, right? The fourth row, fourth and final row, 0, 13, 20, 23, 0, 13, 20, 23, and so forth. And if you do that, you're going to get 367. Okay. So 16 seconds later, the distance between two cars will be around 367 feet. Okay? So this is a very nice problem. All right. Okay, next example. No, not next example. Now, this is the problem of area between y equals f of x and y equals g of x. Area of the region between those two curves. Now, what if you have a two graphs. Let's say C2, let's say this is a bit let's see. Let's say this is D, this area. Now, right-hand side curve is given by x equals f of y. Okay? And this one, x equals g of y. Right-hand side function has a larger x value than left-hand side curve, right? So, same idea. We're gonna approximate this area using, Riemann rectangle. Okay? So, you have to do this. There's mine. So that will be delta y. Alright? Height will be this function value, x coordinate minus this x coordinate, this function value. So instead of f of x and g of x, we have f of y, g of y. So exactly the same idea. So in this case, the area will be from C to D, definite integral of right-hand side function minus left-hand side function. Obviously, we are assuming that always f of y is greater than or equal to g of x on this y interval from C to D. Okay? So, the final example of this section is this. Find the area. Find the area enclosed by y squared equals x plus 1 and y equals x minus 1. Okay. This is a parabola opening right to the right. X-intercept negative. So you can write as y equals y squared minus 1, x equals y plus 1. Okay, we want to use this approach because of this. This is y is not a function of x. X is a function of y. So you have this one, x-intercept minus 1. So 1, 2, 3. Okay. So this one going through like this, and then y plus x minus going through. This one also going through. So we want to find intersection. We want to find the x coordinate of these two intersections because this is the region. This one did not give you intersection point easily. This one, yeah, both of them go through 0, negative. Right? Okay, 0, negative 1. What about the other one? So we have to find the intersection point by solving this system of equations. So x equals this. So y plus 1 equals y squared minus 1. Bring it over here, minus y minus 2. Okay? Negative 2 times 1 will be this, add up to the minus 1. That means this is vector y minus 2, y plus 1. So y equals negative 1 and 2. As we expected, this is negative 1. And this is y equals 2. This right-hand side function can be written this way. X equals y plus 1. This is our f of y. And this one is x equals y squared minus. This is our left-hand side function g of y. So the area is integral from -1 to 2 of this function. Right-hand side function minus left-hand side function with respect to dy. So -1 to 2, y plus 1 minus y squared plus 1, right? So this is -1 to 2, 2 plus y minus y squared dy. So simple polynomial integration. 2y from -1 to 2 plus 1/2 of y squared, -1 to 2, minus 1/3 y cubed, minus 1 to 2. Just definite integral as usual. So this is 2 times 2 minus -1, so 2 plus 1/2, 2 squared, 4. Minus 1 squared is also 1, minus 1. So minus this function that at -1, so minus 1. Alright, be careful here. That's minus 1/3. 2 cubed is 8, minus -1 cubed is -1, minus -1, +1. So you have 3 times 2, 6, plus 3 over 2, 9 over 3 equals 3. 9 over 3 equals 3. So 3 plus 3 over 2, 6 over 2, 3 over 2, 9 over 2. So that's the area. So this, once you set up this integral, everything is just mechanical evaluation of definite integral of simple polynomial. Coming up with this definite integral is the main part. By interpreting this problem as the area of the between two function of y graph. Okay? Alright. That's the end of section 6.1. As I said, this is a rather short section. Alright, I'll see you next time.